Let's take a look at section 4.4, exponential and logarithmic equations. An exponential equation is an equation containing a variable in an exponent. Some equations can be solved by expressing each side of the equation as a power to the same base. Here's the process for that. Rewrite the equation in the form b to the mth power equals b to the nth power. Once you're able to do that, you can then set m equal to n, which will contain the variable, and then you solve for the variable. So let's look at an example of that. Here we have 6 to the x minus 3 over 4 equals the square root of 6. So we're going to use this process on this problem, but we need to recall that the nth root of b equals b to the 1 over n power, and that the square root of b is really a second root of b, where the index 2 is not written. So the square root of b is equal to b to the 1/2 power. So we're able to use that process on this problem by rewriting the square root of 6 as an exponential. So the problem becomes 6 to the x minus 3 over 4 equals 6 to the 1/2. So now the bases are both 6 on either side of the equation, so I set the exponents equal to each other. So I'm going to solve x minus 3 over 4 equals 1/2 by cross multiplying. The top left is multiplied by the bottom right, and the right top is multiplied by the bottom left to give 2x minus 6 equals 4. Add 6 to both sides, and you now have 2x equals 10. Divide both sides by 2, and you have x equals to 5. So the solution set is the set containing 5. Let's look at the fact that we can check these solutions. Let's replace our x with 5. We have 6 to the 5 minus 3 over 4, and we're asking, is that equal to the square root of 6? So it's 6 to the 2/4 equal to the square root of 6. Well, we know that's 6 to the 1/2. We can reduce 2/4 to 1/2, and we know that that's true, that 6 to the 1/2 power is the square root of 6. So let's look at this second example, and we want to solve 8 to the x plus 3 equals 16 to the x minus 1. And we're going to do that by rewriting 8 as 2 cubed and rewriting 16 as 2 to the 4th. And so we have to remember the rules of exponents. And the rule that we're using is that if b to the m is raised to the nth power, then that's the same as b to the m times n. So we're multiplying that 3 times x plus 3 to get 3x plus 9, that 4 times x minus 1 to get 4x minus 4. So now the bases are the same, and we can simply set 3x plus 9 equal to 4x minus 4. Subtract 3x from both sides, add a 4 to both sides of the equation, and we wind up with 13 equal to x. So our solution set is the set containing 13. And we can check that answer also. I'm not going to show the check, but we could check that answer. Most exponential equations can't be easily and precisely rewritten so that each side has the same base. In this type of problem, logarithms can be used to solve the equation. So we're going to isolate the exponential expression, take the common logarithm on both sides of the equation for base 10, take the natural logarithm on both sides for bases other than 10, simplify using log properties, and solve for the variable. So let's solve e to the 1 minus 5s equals 793. And we're going to take, as the process says, the natural log on both sides of the equation. So on the left, we have the natural log of e to the 1 minus 5s. Log properties tell me that simplifies to 1 minus 5s. So I'm using the inverse property of logs and exponentials. The base of the natural log is e, and if I apply a natural log to an exponential whose base is e, I simply get the exponent 1 minus 5s. Let's subtract 1 from both sides and then divide by negative 5, and we have s equals 793, natural log of 793 minus 1 divided by negative 5. And I just want to point out this is natural log, lowercase l, lowercase n. So let's multiply top and bottom by negative 1. And you don't have to do this, but I want to have fewer negative signs. So this becomes negative natural log 793 plus 1 over 5, which I can write as 1 minus natural log 793 over 5. So my solution set is 1 minus natural log 793 divided by 5. And this is the solution set in terms of natural logarithms. Now, what is the decimal approximation for the solution? So I'm going to have to use a calculating device to calculate. I'm going to use Mathematica. And in Mathematica, the natural log is abbreviated log. So that's different from the textbook and most calculators. And notice I get approximately negative 1.14 when I round that result to 2 decimal places. And I can check this solution. So let's actually get the original equation. Plug that solution in and check, and you will get something approximately equal to 793. A logarithmic equation is an equation containing a variable in a logarithmic expression. If a logarithm can be expressed in the form base b log of m equals c, we can solve such equations by rewriting them in exponential form. So our first step is to get the equation in the form the base b log of m equals c. Once we do that, we can rewrite this using the definition b to the c equals m. So let's look at our first problem. Base 4 log of the sum 3x plus 2 equals 3. So notice our m is 3x plus 2, our c is 3, our b is 4. So once we are able to get this in this form, we'll be able to solve for the variable. So our base is 4, our c is our exponent, and that's 3, and our m is 3x plus 2. So 4 to the third equals 3x plus 2. 4 to the third is 64. So 64 equals 3x plus 2. Subtract 2 from both sides, and you get 62 equals 3x. Divide both sides by 3, and you have 62 over 3 equal to x. Now, the thing you have to be careful of is you have to make sure that your x is an x so that m is greater than 0. So in our case, for this problem, m is 3x plus 2. So we need to make sure that's greater than 0. So 3 times 62 over 3 plus 2 needs to be greater than 0 for us to accept this solution. And 64 is the result of replacing x with 62 over 3 and 3x plus 2, and that is greater than 0. So we can accept our solution. And you actually can check these solutions. If the result would have given me something that wasn't greater than 0, then I would have to reject the solution. So I'm going to just show you how you would check it if you wanted to do the check. So the base 4 log of 3 times 62 over 3 plus 2 needs to equal 3. So we're checking this. So the base 4 log of 62 plus 2 needs to equal 3. The base 4 log of 64 needs to equal to 3, and it does. The base 4 log of 64 is the exponent you apply to 4 to get 64, and that exponent is 3. So 3 equal to 3 is a true statement, so my solution set is 62 over 3. Some logarithmic equations can be expressed in the form the base b log of m equals the base b log of n, where the bases on both sides of the equation are the same. Because all logarithmic functions are one-to-one, we can conclude if we can get this form, m equals n. So the first thing we do is express in the form base b log of m equals base b log of n. And if we can get that, we can set m equal to n, solve for the variable, and we need to make sure that our m is greater than 0 and our n is greater than 0 for whatever values we get as solutions. All right, so in example 5, we're going to use the fact that the base b log of m plus the base b log of n is the base b log of m times n. So we're able to rewrite the equation as the natural log of x minus 4 times x plus 1 equals the natural log of x minus 8. So our m is x minus 4 times x plus 1, and we set that equal to our n, which is x minus 8. And we multiply using the distributive property, or FOIL. And notice when we simplify, the left side becomes x squared minus 3x minus 4. The right side is x minus 8. So we subtract x and add 8 to both sides, and we get x squared minus 4x plus 4, which we can factor into x minus 2 times x minus 2 equals 0. So these are repeated factors, so we just need to take one of them, set it equal to 0 using the zero product principle, and x equals 2. Now, we have to check these solutions because we can get something that solves m equal n but doesn't solve our original equation. So let's replace all of our x's in the original equation with 2. And notice that we get the natural log of minus 2 minus the natural log of 3 equals the natural log of negative 6. And we cannot have a log applied to a negative. So we only had one solution. That solution caused me to take logarithms of negative numbers. So there aren't any solutions to this equation. You can never have a log applied to a negative, no matter what the base is. So in solving this problem, I would essentially select that there is no solution.